Thank you all for attending the Water Age and Distribution presentation. Now, our next presenter is going to be Jack Schultz. Jack received his Bachelor's of Science degree in Chemical Engineering from the University of Texas at Austin in 1985. He worked 1 year as a field inspector for the drinking water program in the Tyler Regional Office before transferring to Austin. After arriving at the central office, he performed a variety of duties, including plan review, technical support, and enforcement for almost 30 years. Although Jack resigned from TCEQ in 2013, he continues to work in the Texas Optimization Program as a contractor with the University of Texas at Arlington. He continues to develop various technical assistance and training materials for surface water treatment plant operators and TCEQ staff. He also provides training during TOP activities and works on a variety of special projects. Please welcome Jack Schultz.
Thank you all very much for joining me today. I'm going to try to leave about 5 or 10 minutes at the end for questions. I'm going to cover this topic, but I see a lot of people in this room that have a lot of experience with controlling water age in their distribution system. If I miss something that you think is important, please go to the microphone at the end and augment the presentation. Okay, I want to take advantage of the knowledge we have in the room. What I want to leave with today is just for a couple of take-home messages. Water age affects water quality, as you guys all know, and water age in the distribution system is impacted by the way you operate your storage tanks, how the storage tanks themselves are designed, the size of the lines in your distribution system, their hydraulic capacity, and the water consumption, and the effectiveness of your distribution system flushing program. We're going to try to cover all of these things very quickly today, but like I said, if I miss something, come up at the end and augment. Excessive water age in storage or distribution, as you guys typically experience, results in lower disinfectant residuals throughout the distribution system. And it can be localized, not just the entire system. You can have localized pockets. As the water ages, disinfectant byproduct concentrations gradually rise. So, well, for THM levels, they gradually rise. For HAA levels, they gradually decline. But you might see a difficulty in meeting your THM requirements if the water age in the distribution system gets really excessive. As the disinfectant residual declines, biofilm growth increases. So, in association with the loss of disinfectant residual, especially if you're using chloramines, the chloramines convert and release ammonia. And there are certain types of bacteria that like to eat ammonia. So you'll get an increase in ammonia, oxidizing bacteria, and have nitrification problems in your distribution system. And typically, if you can keep your chlorine residuals, your disinfectant residuals, fairly stable within a range of plus or minus 0.7, 0.8 milligrams per liter, whatever your normal is, you're not going to see a lot of customer complaints because they acclimate to the quality of water they're receiving. The quality changes, you start getting customer complaints. Typical causes of water age in storage. The first thing is the tank really wasn't designed to circulate the water within the vessel. And then there's the operational practices. So the engineer can make a mistake and the operators can make mistakes. And the operators can do a lot of stuff to compensate for the engineer's mistakes, but the engineer can't do a lot to compensate for the operator mistakes. So you guys are kind of the last barrier to letting the water age get real high. There are two kinds of inlet and outlet configurations. There is an internal or external riser, and in this case, this is an external riser where the pipe goes up the side of the storage tank and drops water in the top. And on the internal riser, water goes up to the top of the storage tank, but the top of the internal riser may be somewhat submerged below the water level, the maximum water level. Okay? Both of these things encourage circulation. And it means that the first in water is the first out water. So the oldest water leaves the tank first. Thermal stratification occurs when the temperature of the water inside the tank is not relatively uniform. This happens pretty significantly in tall storage tanks. especially ones with smaller diameters. The sun hits one side of the tank, the hot water kind of rises to the top of the tank where it just keeps getting hotter and hotter and hotter, and the cold water kind of sinks to the bottom of the tank. There's as little as a 2-degree difference in the water temperatures between the top and the bottom can result in this stratification of water. As the water in the top, doesn't matter whether the water comes in at the top or at the bottom, water comes in the top, it's going to be cool, and it will sink to the bottom. So it no longer is a first in, first out situation, it's the last in, first out situation. So thermal stratification is pretty important. The other type of design is the last in, first out, and that's basically a floating tank. Water can come in the bottom on one side and leave the other side, or it can come in the bottom and go out the bottom through the same inlet outlet. It can just basically be a floating tank. The way you can stop the short circuiting in this tank is to put a baffle wall in to force the water that comes in the bottom to go up over the baffle wall in order to get out of the tank. So I can eliminate short circuiting in a bottom in, bottom out tank by installing baffles, either vertical baffles or horizontal baffles. In round tanks, I see circular baffles a lot, okay? So baffling, on the surface water treatment side, baffling is almost essential because you need the contact time. But it's even beneficial on groundwater systems in order to prevent short circuiting. Enhanced mixing. You can put internal air or mechanical mixers in a storage tank to stir the water inside the storage tank and circulate that water. Hydraulic mixing occurs where the water velocity is high enough at the tank inlet to create a circulation pattern within the tank, okay? You're generally not going to get enough velocity at the outlet of the pipe, at the outlet of the tank, to induce much circulation within the tank. What I need is a directed flow, and when you're sucking for your service pumps, water's coming from this little pocket of water right by the suction for the service pumps. There's no drawing from the top of the tank kind of thing. It's all coming from maybe 1.5 feet from the suction pipe for your service pumps. All right. Here's an example of an air bubbler mixer. The air supply comes in the bottom, air gets released through these diffusers. As the air moves up, it sucks the water up with it and creates this circular pattern within the tank. Okay, does that make sense to everybody? Okay, I can do this with a mechanical mixer. It was just easier to draw a picture with air. The other thing that can affect water age in the storage tank is your operating level. For elevated storage tanks and standpipe, it also affects the distribution system pressure, but it even affects it for storage tanks. There are zones within the storage tank that you guys intuitively know exist. There is the ineffective storage where I can't draw the water level any lower than this before my transfer pumps or my service pumps start sucking air, sending water to the distribution system. And I don't want air getting sucked into my service pumps. It causes pinging, and those little air bubbles destroy your impellers on your service pumps, as you guys know, okay? So there's a piece of the ground storage tank where it's just, that water in that tank can't be used, okay? Above that is, some systems want to have a reserve for fire protection so that I never draw into that reserve so that I can always fight a fire, okay? That's usable water. I just don't want to use it, okay? And above that is the equalizing ground storage. It's the water that I can draw down and fill up and draw down and fill up. It's basically the volume that I have available to control water age in my storage tank. Does that make sense to everybody? Excellent. I see a lot of nodding heads. That's really good after lunch. Elevated storage tanks have the same situation. There is an ineffective storage level, and that basically means when the water level in the storage tank gets that low, I can't put 20 psi in the distribution system. And from a regulatory perspective, that's the absolute minimum. From a customer service perspective, that's where customers really start to gripe about, I don't have water pressure. I can't shower. I can't run my washing machine. I can't live life anymore at 20 psi. From a regulatory perspective, it's because That's the pressure at which you dramatically increase the risk of cross-connection and fusion into the storage tank. It's not that 20 psi is always necessary or is a magic number, but as you know, as water flows through the distribution line, it produces a vacuum on the side walls of the pipe. And so the pressure at the side wall may not be 20 psi, it may be 6 psi. And so it can draw water inside your distribution line through a leak, okay? Above that is the emergency storage. Anything below 20 and 35, I can use, but I really can't call it storage. It's not really effective storage. It's where I'm not risking backflow, but I'm not really providing an adequate level of service to my customers. Does that make sense? Okay. Above that, once again, is the fire protection. If you drop below 35 psi, all of a sudden the fire department starts to get a little iffy about the capacity of their fire pumps. They will draw at 20 psi, don't get me wrong, but the output of the pump starts to decline as the suction head on that pump drops. Above that is the equalizing elevated storage tank, and above that is the overflow. And the overflow exists on both of those tanks. And the volume of the tank above the overflow elevation really is not usable storage, because as soon as you try to get the water level above that, water is going to run out of the top of the tank. So this is in an elevated storage tank. This equalizing storage volume is the stuff that you can really concentrate your efforts on adjusting. These other things are kind of constrained by the needs of other customers, or including the regulatory people. Deep cycling of water storage tanks is letting the water level drop as low as you can let it drop while maintaining your desirable distribution pressure. For some of you guys, the magic number is not 35 psi, it's 45 or 50 or 60 psi. And your effective storage is that level that is above that desired operating level, not the 35 psi. I mean, everything between that desirable level and your 35 psi is still usable storage. It's just not going to keep your customers happy. Okay? You use the full equalization volume, whatever that depth is, to let the water level in the tank draw down. So when you have thermal stratification, you're forcing that hot water as low in the tank as you can get it before you put fresh cold water back in top. Now, thermal stratification will still be a problem because the cold water tends to stay at the bottom of the tank. You know, if the inlet pipe is small enough, it will jet and create circulation in the tank. But in some really large storage tanks where I need a 36 or 48-inch drop, distribution outlet, you may not get enough water velocity to cause circulation. You may have to put a mixer in that tank to circulate the water. There's just not enough velocity, okay? Recognize the risk of drawing down into the fire protection volume. It's usable, but it's really not desirable. And avoid the emergency storage volume, that's the 35 to 20 psi number, if at all possible. And never, ever draw down into the unusable. If it's a ground storage tank, you're going to cavitate your service pumps. If it's an elevated storage tank, you're going to risk backflow events. So just don't ever consider that bottom little piece of that sand pipe or elevated tank or ground storage, whatever it is, don't consider that as part of the tank volume. It counts from a regulatory perspective, but just doesn't count as a usable volume for you guys. Does that make sense? I mean, TCEQ excludes the part of the tank above the overflow when they calculate volume, but they don't include the part that in a ground storage tank that you can't actually suck out. I mean, they include that in your volume calculations. And if I'm saying that wrong, somebody from TCEQ better get up at the end of my presentation and correct me, okay? But I've been with TCEQ a long time. I'm pretty confident in that statement. Typical causes of water age and distribution system from a flushing perspective is I don't do a good job of flushing my pipe. I will open up the flush valve and move really old water from this part of the system to this part of the system, but I won't get rid of it, Okay? It just moves the old water around in the distribution system. And there are also seasonal differences in water consumption patterns. The chance of you getting aged water in the winter and spring are a lot higher than the chances of you getting aged water in the summer, because water demand by your customers will keep the water flowing through the pipes. Okay? I mean, you guys see that a lot. Okay? Now you have to fight, in terms of chlorine residuals, you have to fight the fact that warm temperatures cause the chlorine to decay, the disinfectant to decay at a more rapid rate than cold temperatures. So it may not be that you don't ever have low distribution residuals in the summer. You may, but it's probably not due to water age. It's probably due to the temperature and the biological activity and all the other things that can exert a demand. Okay? Assessment tools. Alicia will talk about this a lot when she talks about nitrification action plans. Watch the distribution system residual in the parts of the system that are more susceptible to old water. There was a system that we visited, I don't know, 7 or 8 years ago, where you would think that the north side of town would be the oldest water, when in fact they had improved the distribution system in the periphery of the town, but the center of the town was old 40-year-old pipes. And the diameter of those pipes had gotten smaller and smaller, and business had moved out to the suburbs where all the peoples are. And so their water age in the central part of the system was actually older than the water age at the peripheral parts of the system. So keep an eye on what's going on by measuring the disinfectant residuals. When you're using chloramines especially, as the disinfectant residual drops and the biofilm formation starts to increase, you will see a decline in the pH levels. Because as the bacteria grow, they excrete byproducts, waste products, and the waste products are acidic, okay? So they'll drop the pH of the water slightly. Does that make sense? So your assessment tools will also include pumpage and billing records. What parts of town are using less water on a monthly basis than other parts of town? That will give you some insight into where I need to go monitor my chlorine residuals to make sure water age isn't becoming a problem, and where I have to start doing a more effective flushing program. Residual type and stability. Monochloramine tends to be much, much more stable than free chlorine. Free chlorine is a volatile compound. Chlorine gas is a volatile compound. And whether you're using bleach or whether you're using chlorine gas, you put that into the water, you form hypochlorous acid when you're using free chlorine. There's an equilibrium between hypochlorous acid concentrations and the amount of free chlorine, the gas that gets re-evolved back out of that system. Low pHs, lots of chlorine gas comes off. High pHs, not so much, okay? Monochloramines are stable over a huge range of pHs, okay? All right, temperature. Higher temperatures tend to accelerate residual loss. We've already talked about why. Monochloramine stability. The only place that you can control the stability of your monochloramine is when you actually make the monochloramine molecule. If you make relatively pure monochloramine, the stability of monochloramine is pretty good. But if you don't keep that ammonia to a chlorine ratio right, if you have a lot of excess ammonia going into the distribution system, if your mixing isn't good, you get dichloramine produced, or you get excess ammonia. Dichloramine decays at a much more rapid rate than monochloramine. And free ammonia entering your distribution system, if it's pretty significant, you can end up with nitrification in your distribution system even when your chlorine residuals are 1 milligram per liter or 1.5. Somewhere around 1.5, 1.7, it doesn't really matter what your what your free ammonia levels are. You've got enough chlorine in the water to suppress the growth of ammonia oxidizing bacteria. But you drop below about 1.7, 1.5, that ammonia starts making a difference. You get down below 1, that ammonia level makes a lot of difference. You get down to 0.5, you basically have no control over nitrification anymore. You drop below 0.5, you're going to have a biofilm growth and distribution and a nitrification problem. And it's just the way it is. The benefits of effective chloramine ammonia mixing at the point of application, I can't overemphasize that. If I don't get the chlorine and ammonia completely dispersed, what I do is I have ammonia in the water and then a monochloramine molecule next to it. If I don't get and a free chlorine molecule coming in, if I don't get the free chlorine connected with the ammonia before it will connect with the monochloramine, I'm going to make dichloramine. So what I'm trying to get it to is a monochloramine residual that is about 90% or better of the monochloramine residual. I mean, the monochloramine being 90%, at least 90% of what the total chlorine residual is. I've seen plants that operate really close to 100, and I've seen plants that operate successfully at 80 to 85. So I can't, 90% is a good rule of thumb, but don't take it as gospel. I mean, your system depends, but you get below about 80%, you ought to be looking at, I need to improve something. I need to raise the pH to 8.0 or higher, preferably at least 8.3, so that I slow the reaction down between monochloramine and free chlorine, and I improve the reaction rates between free chlorine and ammonia, okay? I see people giving me the eye. That's an oversimplification, but a pH of 8.3 improves, or higher, really improves monochloramine purity, okay? Free ammonia somewhere between 0.08 and 0.3 if possible. There are places in West Texas that they have something in the water that combines with the free ammonia, and so they tend to leave their treatment plants with a higher free ammonia, measurable free ammonia concentration, and they're still in the 80 to 85, I mean, they're still in the greater than 90%. They try to drop that ammonia level down to 0.1 or 0.15, they start spreading the difference between mono and total. And that's not a good thing. If you need to leave with a 0.3, leave with a 0.3. You get east of 35, you can get those free ammonia levels down with still maintaining your 90% efficiency, you can get those free ammonia levels down to the 0.1 range, okay? Assuming you have good mixing, okay? You can't do it if you don't have good mixing. Does that make sense? All right, if not, that's the microphone at the end. All right, unidirectional flushing. I talked about the movement of old water throughout the distribution system. What you do to prevent that is you isolate parts of the distribution system and force the water to pass through it, all the way from where the old water is, all the way to the end of the flush valve, okay? That's unidirectional flushing. Now, do you have to have pure unidirectional flushing? No. I don't have to move water all the way, old water, all the way to the end of my system. I just have to move it to a flush valve where I can get rid of it, okay? On the parts of the system where the water age is not such a significant problem, I don't have to practice unidirectional flushing. So think of it as semi-unidirectional flushing. Does that make sense? All right, excellent. Flushing effectiveness is impacted by the location and operation of the distribution system valves. I can't tell you how many water systems I've visited over the course of my career that even if they could identify the location of their valves, which they can't always do, nobody's gone out and exercised those darn things. So they go out and put the valve stem on them to isolate that part of the system to unidirectional flushing, and the freaking valve stem breaks off, because it's all corroded and nobody has exercised the valves. When you allocate your resources, if you're fighting a water age problem in distribution that's not tank related, be sure that you have an effective valve exercising and maintenance program, okay? Flushing velocities. Flushing velocities are kind of a thing you gotta deal with. It is really good to have really high flushing velocities because it will scour the pipe. But if you have any sediments in that pipe, when you scour the pipe, you gotta make sure that you completely eliminate all those sediments. Because when you turn that valve off, those sediments that took 3 months to deposit are still floating around in the water, and the customers are gonna see it when they turn their tap on, okay? So there is this balance between, I gotta flush fast enough to get the old water out without wasting a ton of water, And I don't want to flush at a velocity so high that I scour the heck out of my pipes. And you're lucky I caught myself. Flushing volume, time. If you have a long segment of line, you need to flush for longer. You know, it's a function of velocity versus volume of the pipe. Time is determined by how fast the water moves through the pipe and how big the pipe is. Okay? Distribution systems are complex. Here's my flush valve. Here's all the water. This is where water comes into this part of the distribution system. Everywhere water comes in is an open end. I can move water all around in that distribution system, but I can bypass this whole segment if these lines are bigger, okay? Which is the downtown location problem I was talking about. Does that make sense? You got to understand how your distribution system operates. In order to do a unidirectional flushing program, you have to actually plan, okay? It requires a thorough understanding of the distribution network. Hydraulic models are not essential, but they really, really help, okay? They will tell you what parts of the distribution system water is going around because the line sizes are smaller, or the number of customers is lower, or water consumption pattern based on your billing records indicate that these guys just use less water, okay? Up-to-date and accurate maps showing the sizes of the lines and the valve locations, and you got to have sufficient operational valves. If you don't have enough valves, it's going to be really hard to do a unidirectional or even a semi-unidirectional flush. And requires a relatively high level of planning, because when you start doing unidirectional flushing, you're flushing large volumes of water. You don't want to do that between 5 and 7 p.m., okay? All right? You want to try to flush in the early mornings or in the very late evenings if you can, or in the middle of the day. You know, you just try to avoid when everybody's taking a shower or when they turn their sprinklers on, okay? And it requires a pretty hands-on. You've got to go turn the valves. And then you got to remember at the end of the flush, go turn the valves back on. Otherwise, you're going to create all new dead zones that you don't know and you'll never be able to figure out because you think an open valve is actually closed or a closed valve is actually opened. Unidirectional flushing, before you start the flush, you need to prioritize the areas that need to be flushed more frequently and the areas that need to be flushed first. When Alicia talks about the nitrification action plan and flushing for the NAP, she doesn't tell you to start at the end of the system and try to completely flush the whole system through the valves at the end of the system. Start flushing near the plant, get that part of the system with fresh water in it, and then you can take that fresh water out further and further into the distribution system. Did I say that right? I did say that. Okay, very good. Okay. Determine which valves need to be closed in order to force the water in the direction that you want it to go, and decide in the order that the flush valves will be opened and closed. Start closest to the source and move out. Don't start at the far end and try to move back, okay? All you'll end up with is really old water at the far end. Calculating the flow rate needed to clean the line, the feet per second that you need to clean the line. Try not to scour, but try to reduce the time it takes to flush. Calculate the approximate flush time for each pipe segment. Schedule the flushes so that you're not flushing a whole bunch of water all simultaneously. Work yourself through the system. Don't try to do a unidirectional flush all at once, okay? And then try to minimize reverse flow. If there are parts of the system that feed back into the part that you're flushing, be sure you isolate that part of the system that feeds back. Make sure the water goes in the direction that you want. Don't reverse flow in your pipe. Reversing flow in the pipe, the sediment all gets laid down in the direction of the normal flow. You change the direction of the flow, water reverses in that pipe, stirs all that sediment up, okay? So try to keep water going in the same direction that you normally operate the water system in. During the flush, use the opportunity to deep cycle your ground storage tanks. Don't just turn your service pumps on and keep the elevated storage tank completely full while you're flushing. Keep your service pumps off as much as you can to allow that that elevated storage tank to drain down and flush the water. Now, I don't want to move water from the elevated storage tank, reverse flow it into a part of the system that never sees elevated storage tank water. It always sees plant water. Don't try to flush that elevated storage tank back into the plant water part of your system, because it will reverse the flow direction. Collect data, record the starting and ending times of the flush. If you can, get a flow rate, put a flow meter on your flush valve. If you can't, get a pretty good estimate of how big the pipe is and how far out the water goes before it hits the ground, and figure out the approximate flushing velocity. The volume of water that you use during the flush needs to be treated as, I use this water and I know how much, so it doesn't end up showing up on your unaccounted for water. You need to know that I actually use this water. Water Development Board really takes a serious look at unaccounted for water losses. And if you flush 6% of your water and you don't account for it as flushed water, it increases your unaccounted for water loss by 6%. Okay? Take a look at the disinfectant levels and maybe the pH. At the beginning and the end, if you start out with a 1.1 and you end up at the end of the flush with a 1.6, and 1.6 is where you want to be, for God's sake, stop flushing. And try to achieve a water velocity of at least 5 feet per second if you are trying to scour your pipes. If you have a manganese problem in your source water and you are using a sequestering agent instead of removing the manganese from the water, that sequestering agent will hold that manganese in solution for about 14 days. High temperatures, probably closer to 7 days, okay? So you may need to scour that line to get the manganese sediment up off the bottom of the line, or ultimately it will deposit so much that normal usage will stir it up. Now, 5 feet per second is only necessary if you're trying to remove the sediments. Water usage pattern, you have seasonal use. Remember I was telling you that drawing the storage tank down is probably more important during the fall and through spring than it is during the summer months. But look at your average daily demand during whatever period between flushes. Look at your peak daily demand, and look at if you can determine what your peak hourly demand is, that will tell you, I don't want to flush during these periods of time, okay? And billing data. If you don't keep track of all of this data, and it's kind of important that you do, but look at your monthly trends for seasonal changes. I use 30% less water in March than I use in the summer. I'm going to need to increase flushing in March, likely. I'll have to increase flushing in March and reduce flushing in the summer, assuming that your residuals are okay. Bottom line, water age and water quality in the distribution system is impacted by your usage patterns, the design and operation of your storage tank, the effectiveness of your disinfection flushing program, and the stability of the disinfectant residual that you are using. So make pure chloramines if you can. Water usage patterns can, certainly there, but it doesn't impact increase or decrease unaccounted for water. And they rarely require the operators to make multiple changes through the day. Operators rarely have to turn the disinfectant residuals up in the morning and down in the evening, or up in the evening and down in the morning. These are seasonal changes. The water pattern, water age is not I'm going to control it at the production point. I'm going to control it within the distribution system. Water age in the storage tank is impacted by, remember I talked about water quality at the suction, the outlet of the tank? Really doesn't cause circulation within the tank. Water velocity at the inlet can, okay? The location of the inlet and outlet piping, the last in, first out problem, okay? And the height and diameter ratio of the tank. I really didn't talk much about that. But the larger diameter of the tank you have, the more difficult it is to create a circulation pattern in the tank, okay? Really tall tanks have extreme difficulty maintaining circulation patterns. Cold water will enter the top and sink to the bottom and really not create a circulation pattern, okay? Tank mixers. I didn't do a good job of explaining this. They don't reduce the average amount of time in the tank, okay? If I have a really short detention time in the tank, residence time in the tank, and a really long residence time in the tank, I get the same average number as if I circulate the water in the tank. Just some of it's in there a really long time, and some of it doesn't stand there but a minute or two. So the average stays pretty much the same. But it does affect the maximum and minimum amount of time in storage. It doesn't increase the potential for thermal stratification. It actually decreases thermal stratification. It does not increase biofilm. It actually reduces biofilm. Old water sitting at the top of the tank will lose its chlorine residual. We actually went to a water system where the elevated tank floated on the plant, but the plant was really close to the elevated storage tank, and when they turned the service pumps on at the plant, water went right on by the storage tank and out into the distribution system, and that tank stayed full. It may drop a foot before the next service pump cycle, but it doesn't drop a lot because the elevated tanks out in distribution system are dropping. That turns the service pumps on, not the water level in the tank nearest the tank. And that tank had a 0 residual and a nitrate level of 12. I mean, they had left the water in there so long that every little bit of fresh ammonia that they put in the tank was immediately converted to nitrate, and they could never get the nitrate out of the tank. So it just kept accumulating. The concentration just kept accumulating. Okay? Reduce disinfection byproducts by reducing water age. Okay? I have a circle around this thing, the last one, because I don't need to stabilize the residual. I don't need to maintain a stable residual. I just have to get the residual during the flush to the point where I want it to be, because that means that I have flushed the line. I don't need that residual to be there for 8 minutes, because that just means I flushed 8 minutes of unnecessary water out of the line. Okay? Get it where you want it to be and stop. If you have questions about water age and distribution system, there are people in the plan review section that can answer your questions, or the TROT team that can answer your questions. But really, your primary point of contact will be the optimization staff. If you've got some really good field investigators, they will have enough experience trying to help people and cite violations that they might be able to help you, but these guys are the primary points of contact. And there's my contact information, which will be good for the end of the year. In December, I retire, and that number, I will guarantee you, is going to go away. Okay? All right, I've got 3 or 4 minutes for questions or comments that you want to make that I need to correct. Come on up and give it to me. Thank you.
One really quick thing, that magic 1.7 mono that you think is going to kill all the bugs, it'll do that up to a point where the bugs start really growing, at which point, who knows. If the bugs are this high and your disinfectant's this high, you're going to have to put more disinfectant.
Once you see the mono residual drop below 1.7 and your ammonia level starts to drop, and she'll talk about this during nitrification. When your ammonia level starts to drop in distribution residual, you've got the beginning of nitrification.